So where can we use electrolysis? Well, the first is that we can electroplate items, which means that we can put something like a steel cathode in, but we could then not use sodium chloride, let's say copper chloride or nickel nitrate or something like that, and then the metal will plate on the outside of that cathode. Purification of metals, for example copper, what they do is they use an impure copper sample, they put in a potential difference of about 0.34, so that'll drive this reverse reaction to happen, and then simultaneously you'll run this copper on the other electrode. The ions will go in the opposite direction. Why? Because we're supplying electrons over there, so we land up driving a particular reaction to occur, and then the production of chlorine is the other process that can be done, and we'll talk about that in a whole lot more detail in a second. First one I'm going to look at is aluminium. Aluminium is amazing because it's low density, it's got high strength, it's very useful because of the fact that it seems not to rust. It turns out that actually aluminium does rust. It just rusts so fast that it protects itself. It makes its own little sheath around itself. But it's used in a multitude of different items. So aluminium is much more reactive than you might imagine, and actually it reacts rapidly with oxygen in the air to form an unbroken layer of aluminium oxide on the outside of something, and that prevents further reaction with oxygen. Unlike iron, which breaks up all the time when it forms iron oxide, and that's we call corrosion, or we call that rust. Turns out aluminium oxide does oxidize, but it does it very quickly, and it forms a nice clean layer on the outside. So how do we get aluminium? Very useful stuff. The first examples of aluminium were prepared with aluminium chloride, and it was a bit more complicated than it is now. And you needed aluminium against potassium or with sodium in order to break it up. Today, what do? They take aluminium from its rock ore, which is called bauxite, and bauxite is mainly found in Australia, and then they break it up. You want to get aluminium oxide by electrolysis. So what happens is the alumina melts at very, very high temperatures. So that's not helpful because it just costs too much money to get up to that temperature. But if you mix bauxite with this stuff over here, which is cryolite, it's sodium, aluminium, and fluorine, and then you mix it into the cryolite, you can get the melting point right down to 950 to 1000 degrees centigrade, which is half of that, which means half the energy is going to be required. What happens there is both the anodes and the cathodes are made of carbon. There are many cells, and they're connected in series, each operating at about 5 volts and about 150,000 amps. And this is a very, very electricity-rich process, and it's not great in the sense that we do it in South Africa and it causes a lot of carbon dioxide emissions. And we pass the current through, and we have to keep this melted all the time. And what happens is the aluminium 3+ gains electrons and becomes aluminium metal. We siphon that off the bottom of the system, and that's obviously at the cathode. Why is it at the cathode? Because that's reduction, gaining of electrons. At the anode, which is the positive, the negative oxides join and they form oxygen, but immediately oxygen reacts with the carbon in the electrode and forms carbon dioxide. So this is another pollutant. Firstly, we're using a lot of electricity. Secondly, we're making more carbon dioxide. So this stuff is really not great. Also, we're busy destroying our carbon anodes, and they need to be replaced at regular intervals. So what's happening overall for extraction of aluminium is the aluminium oxide forms aluminium with the help of the carbon electrode, forms aluminium and carbon dioxide. So we put the molten cryolite into the solution over here. This whole vessel is made of carbon, and that is going to be your negative electrode, and the aluminium is going to be attracted, Al3+, gets attracted there and forms aluminium. It's reduction, so that's your cathode. And then you have got these little anodes over here. They attract the oxide ion, and then you land up with carbon dioxide. So we get aluminium and carbon dioxide. it's very important to South Africa's economy because we do make a lot of aluminium, and that was historically because we had a lot of very cheap electricity, and we still have relatively cheap electricity in the world. We bring all this bauxite on a ship over from Australia, and then we refine it into aluminium and then send the aluminium back to Australia. To produce aluminium, it uses a lot of electricity, and you need for about a ton of aluminium, you need 15,000, basically 16,000 kilowatt hours. The carbon dioxide produced during electrolysis process and in generating electricity increases South Africa's greenhouse effect. By recycling aluminium, you save 8 tons of bauxite, 4 tons of other chemicals, and about 14,000 kilowatt hours of electricity. So it really is important to recycle aluminium cans. The energy to produce the metal by recycling is 5% of what it is to extract the metal from its ore, and greenhouse emissions are reduced down to 5% of what they were. Then we've got another thing where we want to, this is your chlorine cell. We're trying to make chlorine, and the way that we do that is by breaking up sodium chloride. And the first way they used to do it was using a mercury cell. The mercury cell is basically redundant now because mercury is a problem. You get mercury emissions. But in the old days, that was called the Kastner process, and this is how it worked. We had titanium anodes, and they were placed in a sodium or potassium chloride solution, and the chlorine was released at the titanium anodes, and then sodium or potassium dissolved into the mercury and formed an amalgam, because that's metal and metal, so it's basically an alloy that was formed, an amalgam in a liquid form, and then they recycled the mercury and they used it again. The problem with the mercury is it was not very efficient, and of course mercury emissions are a problem because mercury is a heavy metal, which means that it causes heavy metal poisoning. The overall cell reaction looked like this. Sodium chloride plus water gave me sodium plus hydroxide plus hydrogen plus chlorine. Let's look at the half reactions with that. Now they put a current through this system, and as we've said, we're going to take the chloride ion and we are going to turn it into chlorine. So that reaction goes backwards. I'm putting electricity in, so this is fine, and the water to hydrogen and hydroxide goes forwards. What you will notice is that the sodium, the Na plus ion, is in there, but it is even more difficult to, it is more likely to be oxidized. In other words, the water over here is more likely to be reduced, and therefore it is not going to reduce the sodium. It's going to reduce the water. So we've got that reaction going backwards and that one going forwards. So what do we have? We have 2 Cl minuses becoming Cl2 plus 2 electrons. Simultaneously, I'm going forwards on the other side. The water, because this is all happening in a solution, 2 electrons gives me hydrogen and OH minus. So what is going to happen, sorry, that H looks terrible, is my electrons cancel out, and I'm left with 2 chlorides plus 2 H2Os, gives me chlorine and hydrogen and OH minus, 2 of them, sorry. And then the sodium is just a spectator ion. Na, 2 NAs there, 2 NAs here, and that lands up being the overall balanced equation. This equation is true for all of our chlorine productions. So this is just a diagram of the mercury amalgam. Brine is a name we give a sodium chloride or potassium chloride solution. It's called the brine, and the solution's in there, and the chlorine comes off at the anode, and the mercury and sodium go off at the cathode. The advantage here is I don't form sodium hydroxide. The mercury just seems to disappear with, at least the sodium just disappears with the mercury. I can then remove the sodium and I will form sodium hydroxide separately. But one of the problems with this process is that we keep making sodium hydroxide. The diaphragm cell was an upgrade on the mercury cell, and it had a diaphragm, in other words a membrane of, well, it's not a membrane, a partition separating the anode and the cathode, and therefore the chlorine that formed at the anode didn't remix with sodium hydroxide, because that's a bit defeatist, otherwise we just land up going round and round in circles. and the hydrogen. The brine was fed through the anode compartment and it flowed through the diaphragm to the cathode, where sodium hydroxide was produced. This method forms quite dilute sodium hydroxide. That's not nice, because if we want to sell this stuff, we really want it to be quite concentrated. It operates at a lower voltage than the mercury cell, so that was a good thing, and that causes energy savings. But large amounts of steam were required, and it has to be evaporated to concentrate up this dilute sodium hydroxide that you're making. Notice the equation is exactly the same. Here's a picture of the diaphragm cell, and here's the diaphragm that's in the middle, and we're pumping the brine in. We land up with chlorine being produced at the anode, and then on the cathode we land up forming sodium hydroxide that is dilute and a little bit of hydrogen gas. This is still not optimal. They've made an advance on that, and it's called the membrane cell, where this diaphragm only allows certain ions through. So the membrane cell also has two compartments, but it's a cation permeable membrane that acts as the ion exchanger. So I put saturated sodium or potassium hydroxide is passed through the anode compartment and chlorine is formed. Sodium or potassium hydroxide is formed and circulates in the cathode compartment. The good news is I get 32% concentrated potassium or sodium hydroxide, so that is much better. What's the disadvantage? You need very, very pure brine. So over here what happens is in comes the sodium chloride. We make chlorine, but the chloride ion can't go to the other side, so only the sodium ion comes to the other side, which means you land up with much more concentrated sodium hydroxide coming out there, and that is a much better, because this is, remember, a cation only permeable membrane. So that is more efficient all round.